What if the next chapter of human history wasn't written on Earth, but on a planet orbiting a star just 4.37 light-years away? Imagine a future where humanity's home isn't just this pale blue dot, but a new world in the Alpha Centauri system, the closest star system to our own. This isn't science fiction anymore. It's a tantalizing possibility that could redefine what it means to be human. But here's the catch: getting there is no small feat. The challenges are immense, from the mind-boggling distances to the technological leaps we'd need to make. Yet the rewards could be even greater: a new Earth, a fresh start, and the survival of our species among the stars. So, could we colonize Alpha Centauri today? Let's dive into the science, the challenges, and the incredible possibilities of this interstellar dream. Stay with us, because by the end of this video, you'll see why this might not just be a distant fantasy, but a mission humanity could one day achieve. Now, turning to the Alpha Centauri system itself, let's break down what makes this star system so fascinating and why it's our best shot at finding a new home among the stars. Alpha Centauri isn't just one star, it's a trio of stars, each with its own unique characteristics. The two brightest stars, Alpha Centauri A and B, form a binary pair orbiting each other in a cosmic dance. Alpha Centauri A is remarkably similar to our Sun, both in size and brightness, while Alpha Centauri B is slightly smaller and cooler. But the real star of the show, pun intended, is Proxima Centauri, a red dwarf star that's part of the same system but lies a bit farther out. Proxima Centauri is special for one big reason. It's home to Proxima B, an exoplanet that sits within the star's habitable zone. This means it's at just the right distance to potentially have liquid water on its surface, a key ingredient for life as we know it. Proxima B is roughly 1.3 times the mass of Earth, making it a prime candidate for colonization. But before we get too excited, there's a catch. Proxima Centauri is a red dwarf, which means it's much cooler and dimmer than our Sun. This could lead to some extreme conditions on Proxima B, like tidal locking, where one side of the planet always faces the star, creating a scorching hot day side and a freezing cold night side. And then there's the distance. Even though Alpha Centauri is the closest star system to Earth, it's still 4.37 light-years away. To put that into perspective, if we were to travel at the speed of our fastest spacecraft today, it would take tens of thousands of years to get there. That's a journey longer than all of recorded human history. So while Proxima B might be our most promising target, the challenges of reaching it are nothing short of monumental. But as we'll see, the dream of colonizing Alpha Centauri isn't just about the destination. It's about the journey and the incredible advancements we'd need to make along the way. Now, turning to the challenges of interstellar travel, let's dive into the immense hurdles we'd face on a journey to Alpha Centauri. The first and most obvious challenge is the sheer distance. At 4.37 light-years away, even traveling at the speed of light, which is the fastest anything can move in the universe, it would take over 4 years to reach our destination. But here's the catch: our current spacecraft are nowhere near that speed. The fastest spacecraft ever built, like NASA Parker Solar Probe, can reach speeds of up to 430,000 miles per hour. Sounds impressive, right? But at that pace, it would still take tens of thousands of years to reach Alpha Centauri. That's longer than the entire history of human civilization. Then there's the energy problem. To accelerate a spacecraft to even a fraction of the speed of light would require an enormous amount of energy, far beyond what our current technology can provide. Chemical rockets, the kind we use today, simply don't have the power to get us there in a reasonable time frame. Even ion drives, which are more efficient, would take centuries to make the trip. And let's not forget the fuel itself. Carrying enough fuel for such a journey would add significant weight to the spacecraft, making it even harder to accelerate. It's a vicious cycle that highlights just how far we are from making interstellar travel a reality. but the challenges don't stop at physics and engineering. There's also the human factor to consider. A journey to Alpha Centauri would likely take multiple generations, meaning the people who arrive wouldn't be the same ones who left. This raises profound questions about the psychological and biological toll of such a voyage. How would humans cope with living in confined spaces for decades or even centuries? How would we maintain mental health, social structures, and a sense of purpose over such a long period? And what about the biological challenges, like the effects of prolonged exposure to microgravity and cosmic radiation? These are questions we're only beginning to explore, but they're just as critical as the technological ones. As we move forward, it's clear that the dream of reaching Alpha Centauri isn't just about building faster ships or finding new energy sources. It's about rethinking what it means to be human in the vastness of space. The journey itself would be as much a test of our resilience and ingenuity as it would be a leap into the unknown. And while the challenges are daunting, they're also what make the idea of interstellar travel so compelling. After all, it's not just about reaching another star, it's about pushing the boundaries of what we thought was possible. Now turning to the current state of spacecraft technology, let's take a closer look at what we have today and why it falls short for a journey to Alpha Centauri. The most common propulsion systems we use right now are chemical rockets, like the ones that power missions to the International Space Station or the Moon. These rockets work by burning fuel to create thrust, and while they're great for short trips within our solar system, they're simply not efficient enough for interstellar travel. The problem is that chemical rockets require a huge amount of fuel to generate the necessary speed, and carrying that fuel adds weight, which in turn requires even more fuel. It's a cycle that makes reaching even a fraction of the speed of light practically impossible with this technology. Then there are ion drives, which are a step up in terms of efficiency. Instead of burning fuel, ion drives use electricity to accelerate charged particles, creating a steady but low-thrust propulsion. This makes them ideal for long-duration missions within our solar system, like NASA's Dawn mission to the asteroid belt. However, while ion drives are more efficient than chemical rockets, they still lack the power needed for interstellar travel. Even with continuous operation, an ion-driven spacecraft would take centuries to reach Alpha Centauri, far longer than a human lifetime. Another promising technology is solar sails, which harness the pressure of sunlight to propel a spacecraft. These sails are lightweight and don't require fuel, making them an attractive option for long-distance travel. In fact, projects like the Breakthrough Starshot initiative are exploring the possibility of using laser-powered solar sails to reach Alpha Centauri within a few decades. But even here, there are significant challenges. Solar sails rely on external energy sources like lasers to achieve high speeds, and building a laser system powerful enough to propel a spacecraft across interstellar distances is still beyond our current capabilities. So, what would it take to make interstellar travel feasible within a human lifetime? The answer lies in breakthroughs that go beyond our current understanding of propulsion. We'd need technologies that can generate enormous amounts of energy without the limitations of fuel or external power sources. Concepts like nuclear pulse propulsion, which uses controlled nuclear explosions to propel a spacecraft, or antimatter engines, which harness the energy released when matter and antimatter collide, could potentially provide the necessary thrust. But these ideas are still in the realm of theory, and turning them into practical solutions will require decades of research and innovation. In short, while our current spacecraft technology has taken us to the Moon, Mars, and beyond, it's not enough to take us to the stars. To reach Alpha Centauri within a human lifetime, we'll need to rethink propulsion entirely, pushing the boundaries of science and engineering in ways we've only begun to imagine. The journey may be daunting, but it's also an opportunity to redefine what's possible and to take the next giant leap for humanity. Now turning to the realm of breakthrough propulsion concepts, let's explore some of the most futuristic ideas that could one day make interstellar travel a reality. One of the most intriguing possibilities is nuclear pulse propulsion, a concept that dates back to the mid-20th century. The idea is to use controlled nuclear explosions to propel a spacecraft forward. Imagine a series of small nuclear detonations occurring behind the spacecraft, each one pushing it forward with incredible force. While this might sound like science fiction, it's a concept that has been seriously studied, most notably in Project Orion, a Cold War-era initiative. Theoretically, nuclear pulse propulsion could achieve speeds high enough to reach Alpha Centauri within a human lifetime. However, the challenges are immense. Building a spacecraft capable of withstanding repeated nuclear blasts, managing the radiation risks, and ensuring the safety of such a system are just a few of the hurdles that would need to be overcome. Another groundbreaking idea is the antimatter engine. Antimatter is the opposite of normal matter, and when the two come into contact, they annihilate each other, releasing an enormous amount of energy. In fact, antimatter is the most energy-dense substance known to science. An antimatter engine would harness this energy to propel a spacecraft at speeds approaching a significant fraction of the speed of light. Theoretically, this could reduce the travel time to Alpha Centauri to just a few decades. But here's the catch: producing and storing antimatter is incredibly difficult and expensive. Currently, we can only create tiny amounts of antimatter in particle accelerators, and storing it requires advanced magnetic fields to prevent it from coming into contact with normal matter. Despite these challenges, research into antimatter propulsion continues, with scientists exploring ways to make it more practical and cost-effective. Then there's the concept of warp drives, popularized by science fiction but rooted in real scientific theory. A warp drive would work by bending the fabric of space-time itself, creating a warp bubble that allows a spacecraft to travel faster than the speed of light without actually breaking the laws of physics. This idea is based on Einstein's theory of general relativity, which suggests that space-time can be warped by massive amounts of energy. While the energy requirements for a warp drive are currently beyond our capabilities, some estimates suggest we'd need the energy equivalent of a star. Scientists are actively exploring ways to make this concept feasible. For example, researchers are investigating whether negative energy or exotic matter could be used to create the necessary warp bubble. While warp drives remain a distant dream, they represent a fascinating area of research that could one day revolutionize space travel. These breakthrough propulsion concepts are not just theoretical musings, they are the focus of ongoing research and experimentation. Projects like NASA's Innovative Advanced Concepts program are funding studies into nuclear pulse propulsion, antimatter engines, and even warp drives. Private initiatives such as the Breakthrough Starshot project are also pushing the boundaries of what's possible, exploring laser-powered propulsion and other innovative ideas. While the challenges are significant, the potential rewards are even greater. Developing these technologies could not only enable us to reach Alpha Centauri, but also open up the entire galaxy to exploration and discovery. As we look to the future, it's clear that the journey to the stars will require more than just incremental improvements to existing technology. It will demand bold new ideas, groundbreaking research, and a willingness to tackle challenges that seem insurmountable today. But as history has shown, humanity's greatest achievements often begin as impossible dreams. The quest for interstellar travel is no different. It's a challenge that calls on us to push the limits of science, engineering, and imagination. And who knows, the breakthroughs we make along the way could transform not just space travel, but life on Earth as well. Now turning to the critical challenge of life support and sustainability, let's explore what it would take to keep a crew alive and healthy on a multi-generational voyage to Alpha Centauri. One of the most pressing issues is creating a self-sustaining ecosystem that can provide everything the crew needs to survive: air, water, food, and waste management. without relying on resupply from Earth. This is no small feat, as even the smallest imbalance in such a system could have catastrophic consequences. First, let's consider life support systems. On Earth, we take for granted the natural processes that keep our air breathable and our water clean. In space, these processes must be replicated artificially. Advanced air filtration systems would be essential to remove carbon dioxide and replenish oxygen, while water recycling systems would need to purify and reuse every drop of water, from drinking supplies to sweat and even urine. Closed-loop systems, where waste is continuously recycled into usable resources, would be the backbone of such a mission. Experiments like Biosphere 2, which attempted to create a self-sustaining environment on Earth, have taught us valuable lessons about the complexity of these systems. While Biosphere 2 ultimately faced challenges, it highlighted the importance of balancing every element of the ecosystem, from plant growth to microbial activity. Food production is another major hurdle. Growing enough food to sustain a crew for decades would require innovative solutions such as hydroponics or aeroponics, where plants are grown without soil using nutrient-rich water or mist. These systems would need to be highly efficient, producing a steady supply of fruits, vegetables, and possibly even protein sources like algae or lab-grown meat. However, growing food in space comes with its own set of challenges, from limited space and energy to the effects of microgravity on plant growth. Researchers are already experimenting with these technologies on the International Space Station, but scaling them up for a multi-generational voyage would require significant advancements. Waste recycling is equally critical. On a journey to Alpha Centauri, there's no option to dispose of waste. Everything must be reused. This means developing systems that can break down organic waste into nutrients for plants, convert plastic and other materials into reusable forms, and safely manage hazardous waste. The psychological well-being of the crew is another vital consideration. Spending decades in a confined space far from Earth could take a toll on mental health. Ensuring the crew has access to recreational activities, social interaction, and mental health support would be essential to maintaining morale and productivity. The lessons from Biosphere 2 and other closed-loop experiments remind us that creating a self-sustaining ecosystem is as much an art as it is a science. It requires meticulous planning, constant monitoring, and the ability to adapt to unforeseen challenges. As we look toward the stars, the development of these systems will be just as important as the propulsion technologies that get us there. After all, what good is reaching Alpha Centauri if we can't survive the journey? Now turning to Proxima B, the exoplanet orbiting Proxima Centauri, let's explore whether this distant world could truly become humanity's next home. Proxima B is often described as a potential Earth-like planet, but what does that really mean? Located just over 4 light-years away, it sits within the habitable zone of its star, where temperatures could allow liquid water to exist, a key ingredient for life as we know it. With a mass about 1.3 times that of Earth, Proxima B is likely a rocky planet, making it a promising candidate for colonization. But before we pack our bags, there are some significant challenges to consider. One of the most intriguing yet daunting aspects of Proxima B is its potential tidal locking. This means one side of the planet could permanently face its star, while the other side remains in perpetual darkness. Imagine a world where one hemisphere is scorching hot and the other is freezing cold. The narrow strip of land between these extremes, known as the Terminator Zone, might be the only habitable area. Building a colony here would require advanced technology to manage extreme temperature differences and create stable living conditions. Another major challenge is the intense radiation from Proxima Centauri, a red dwarf star known for its frequent and powerful solar flares. These flares bombard Proxima B with high levels of radiation, which could strip away its atmosphere over time and make the surface inhospitable. To survive, colonists would need robust shielding, possibly underground habitats or specially designed structures to protect against radiation exposure. This adds another layer of complexity to the already monumental task of settling on an alien world. The surface conditions of Proxima B remain largely unknown. Is it covered in oceans, deserts, or rocky terrain? Does it have an atmosphere thick enough to support life? These are questions we can't yet answer with certainty. Future missions like the James Webb Space Telescope may provide more insights, but for now we can only speculate. What we do know is that colonizing Proxima B would require not just technological innovation, but also a willingness to adapt to an environment that could be vastly different from Earth. Despite these challenges, Proxima B represents a tantalizing possibility. It's the closest potentially habitable exoplanet to Earth, and its discovery has reignited dreams of interstellar colonization. As we continue to study this distant world, we may uncover new ways to overcome its obstacles and turn it into a new home for humanity. The journey to Proxima B won't be easy, but the rewards could be extraordinary. With the next phase of the journey in sight, let's now imagine what it would take to build a colony on this alien world. Now turning to the monumental task of building a colony on Proxima B, let's envision what it would take to transform this distant world into a new home for humanity. Establishing a settlement here would require cutting-edge technology and innovative solutions to overcome the planet's harsh conditions. Advanced robotics would play a crucial role, as they could perform tasks too dangerous or complex for humans, such as constructing habitats, mining resources, and maintaining infrastructure in an environment where every mistake could be life-threatening. Three-dimensional printing, or 3D printing, would also be essential. Imagine using local materials from Proxima B to print everything from tools to entire buildings. This technology could reduce the need to transport heavy equipment from Earth, saving time and resources. Autonomous construction systems would further streamline the process, allowing machines to work around the clock without human supervision, ensuring that the colony grows efficiently and sustainably. One of the most critical challenges would be creating a breathable atmosphere. Proxima B's current atmosphere, if it exists, may not be suitable for human life. Colonists might need to engineer an artificial atmosphere or find ways to terraform the planet over time. This could involve introducing microorganisms to produce oxygen or deploying large-scale atmospheric processes to filter and replenish the air. Managing resources would also be a constant concern, as every drop of water and every ounce of food would need to be carefully conserved or produced locally. Protecting colonists from radiation and extreme weather would require innovative solutions. As we've discussed, Proxima Centauri's frequent solar flares pose a significant threat. Habitats might need to be built underground or shielded with thick layers of radiation-resistant materials. Extreme temperature differences between the planet's day and night sides would also demand advanced climate control systems to maintain stable living conditions. Despite these challenges, the dream of building a colony on Proxima B is not out of reach. With the right combination of technology, ingenuity, and determination, humanity could one day call this alien world home. As we continue to explore the possibilities, the next step in our journey takes us to the ethical and philosophical questions surrounding interstellar colonization. What does it mean to become an interstellar species, and who gets to decide the future of humanity among the stars? Now turning to the ethical and philosophical considerations of colonizing Alpha Centauri, we must confront some of the most profound questions humanity has ever faced. Who gets to decide who embarks on this journey? Will it be a select group of scientists, engineers, and pioneers? Or should the opportunity be open to anyone willing to take the risk? The idea of choosing who gets to go raises concerns about fairness, privilege, and the potential for creating a new kind of inequality among the stars. Another critical question revolves around the rights of future generations born during the journey or on Proxima B. These individuals would have no say in the decision to leave Earth, yet their lives would be shaped entirely by the choices made today. How do we ensure their well-being and autonomy in a society that exists millions of miles from Earth? The concept of consent becomes murky when considering those who will inherit this interstellar legacy. Then there's the possibility of encountering extraterrestrial life. If Proxima B or another planet in the Alpha Centauri system harbors life, even in microbial form, what responsibilities do we have as visitors? Colonization could unintentionally harm or destroy these life forms, raising ethical concerns about our right to interfere with ecosystems beyond our own. The idea of becoming an interstellar species comes with the weight of stewardship, not just for our own survival, but for the preservation of any life we may find. Philosophically, the act of leaving Earth to settle another star system forces us to reconsider what it means to be human. Are we Earth-bound creatures, or is our destiny written in the stars? Becoming an interstellar species would mark a profound shift in our identity, challenging us to adapt not just physically, but culturally and spiritually. It raises questions about our place in the universe and whether we are destined to explore, connect, and perhaps even coexist with other forms of life. As we grapple with these ethical and philosophical dilemmas, it's clear that colonizing Alpha Centauri is not just a technological challenge, it's a moral and existential one. The decisions we make today will echo across generations, shaping the future of humanity in ways we can only begin to imagine. With these questions in mind, we now turn to the economic and political challenges that stand between us and the stars. Now turning to the economic and political challenges of colonizing Alpha Centauri, we must confront the staggering costs and complexities of such an ambitious endeavor. The financial investment required for interstellar travel and colonization is almost beyond comprehension. Estimates suggest that developing the necessary technology, building spacecraft capable of reaching Alpha Centauri, and establishing a sustainable colony could cost trillions of dollars. This raises the question of who will fund such a project. Will it be a single nation, a coalition of countries, or a partnership between governments and private companies? The scale of the investment demands unprecedented levels of international collaboration, as no single entity could shoulder the burden alone. The political challenges are equally daunting. Coordinating a global effort of this magnitude would require overcoming decades of geopolitical tensions and rivalries. Nations would need to set aside differences and work together toward a shared vision of humanity's future. This level of cooperation has rarely been achieved in human history, and the stakes have never been higher. The project would also need to navigate complex legal and regulatory frameworks, from space treaties to resource allocation agreements. Who owns the rights to Proxima B or any resources we might find there? These questions could spark conflicts if not addressed with foresight and diplomacy. Private companies like SpaceX are already playing a pivotal role in advancing space exploration, and their involvement in an Alpha Centauri mission could be transformative. Companies like these bring innovation, efficiency, and a willingness to take risks that governments often avoid. However, relying too heavily on private entities raises concerns about accountability and equity. Should the future of humanity's expansion into the stars be driven by profit motives, or should it remain a collective endeavor guided by the common good? Despite these challenges, the potential benefits of colonizing Alpha Centauri are immense. The technological advancements required for such a mission could revolutionize industries on Earth, from energy production to materials science. The knowledge gained from exploring and settling another star system could propel humanity into a new era of discovery and innovation. Moreover, establishing a colony on Proxima B would serve as a safeguard for the survival of the human species, protecting us from existential threats like climate change, pandemics, or asteroid impact. As we weigh these economic and political hurdles, it's clear that the journey to Alpha Centauri is not just a scientific or engineering challenge. It's a test of our ability to unite as a species and work toward a common goal. The decisions we make today will determine whether we can overcome these obstacles and take our first steps toward becoming an interstellar civilization. With these considerations in mind, we now turn to the importance of inspiring the next generation to make this dream a reality. Now turning to the importance of inspiring the next generation, we must recognize that the dream of colonizing Alpha Centauri will not become a reality without the passion, creativity, and dedication of young minds. The journey to the stars is not just a challenge for today's scientists and engineers, it's a call to action for the students, dreamers, and innovators of tomorrow. To make interstellar colonization possible, we need to ignite a spark of curiosity and ambition in young people, encouraging them to pursue careers in science, technology, engineering, and mathematics or STEM. Education plays a pivotal role in this effort. Schools and universities must provide students with the tools and opportunities to explore the wonders of space and the technologies that could take us there. Hands-on learning experiences such as robotics competitions, space simulation programs, and astronomy clubs can help students see the real-world applications of STEM fields. By connecting classroom lessons to the grand vision of interstellar travel, we can inspire students to dream big and work hard to achieve those dreams. Public engagement is equally important. Space agencies, private companies, and educational institutions must collaborate to bring the excitement of space exploration to the public. Events like space expos, planetarium shows, and citizen science projects can make the cosmos feel accessible to everyone, not just scientists. When young people see the incredible achievements of missions like the Mars rovers or the James Webb Space Telescope, they begin to understand that the stars are not out of reach, they are a destination waiting to be explored. Visionary leadership is also essential. We need leaders who can articulate a compelling vision of humanity's future among the stars and inspire others to join the effort. Figures like Elon Musk, who has made space exploration a central mission of his companies, show how bold ideas can capture the imagination of millions. But leadership doesn't just come from the top, it can come from teachers, mentors, and even peers who encourage others to think beyond the limits of our planet. The journey to Alpha Centauri will require more than just advanced technology and international cooperation. It will require a generation of thinkers and doers who are willing to push the boundaries of what's possible. By investing in education, fostering public enthusiasm for space, and cultivating visionary leaders, we can ensure that the dream of interstellar colonization lives on in the hearts and minds of the next generation. With their passion and ingenuity, the stars may one day be within our reach. Now turning to the conclusion of our journey, let's reflect on the incredible challenges and possibilities we've explored in the quest to colonize Alpha Centauri. From the immense distances and technological hurdles to the potential of Proxima B as a new home for humanity, the dream of reaching the stars is as daunting as it is inspiring. We've discussed the need for breakthroughs in propulsion, life support systems, and sustainable ecosystems, as well as the ethical, economic, and political considerations that come with such a monumental endeavor. Yet, despite these challenges, the vision of humanity becoming an interstellar species remains a powerful and unifying goal. The journey to Alpha Centauri is not just about science and technology, it's about the human spirit. It's about our curiosity, our resilience, and our ability to dream beyond the limits of our world. It's about inspiring the next generation to take up the mantle of exploration and push the boundaries of what's possible. As we stand on the brink of a new era in space exploration, the question is not just whether we can reach Alpha Centauri, but whether we have the courage and determination to make it happen. So, what do you think? Could humanity colonize Alpha Centauri in your lifetime? Imagine a future where the stars are no longer distant points of light, but destinations waiting to be explored. Share your thoughts in the comments below. Do you believe we can overcome the challenges and make this dream a reality? And if you're as excited about the possibilities as we are, don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss an update on humanity's journey to the stars. Together, let's keep dreaming, exploring, and reaching for the cosmos. The future is out there. Let's make it ours.